So far, we've discussed deep learning algorithms that only work on inputs with a fixed size. But what if we want to learn a model on inputs that vary in size, like sequences? We'll talk about how recurrent neural networks can help us achieve this goal. Then we'll talk about the LSTM, a special version of the RNN. So let's get on with the RNN architecture. RNNs are mainly useful for sequential data, which includes time series data like stock prices. In addition, RNNs are widely used for natural language processing, like speech analysis, sentiment analysis, and language translation. A recurrent neural network is very similar to a feed-forward neural network, except it also has connections pointing backwards. We can see this on the left diagram. To make the description more clear, we can unroll the network on the left to produce the diagram on the right. Keep in mind that the diagram on the left and the diagram on the right are the same thing. Here, we see that the RNN receives inputs, produces outputs, and sends the output back into itself to prepare for the next inputs. More specifically, at time step t, it receives the output from itself at time step t minus 1. Along with that, it also takes the new input xt to produce the output yt. And lastly, the output is fed back into itself to prepare for the next input xt plus 1. In the RNN architecture, there are two sets of weights, one corresponding to the new inputs x's and the others for the output of the previous time step y's. Extending this to multiple neurons is rather simple. It's just like extending a single neuron to multiple neurons for feed-forward neural networks. And we can stack multiple layers simply by taking the output y's and feeding that to the next layer of neurons in the RNN. Now let's discuss the LSTM architecture. Although RNNs are able to take sequences of arbitrary length, RNNs have trouble learning when the length of the sequence is too long. This is because long sequences slow down training by a lot, and it's not possible to parallelize RNN training across time steps. In addition, when training on long sequences, the memory of the initial inputs are slowly forgotten as we go through the time steps. This can be devastating because signal from the earlier input in the sequence can be very important to the task you are trying to solve. The long short-term memory cell helps address the second issue by learning how to recognize important inputs, store it in the long-term states, learn to preserve it for as long as is needed, and learns to extract the inputs when it's needed. Experimentally, LSTMs have been shown to perform better, converge faster during training, and more effectively detect long-term dependencies. So how does the LSTM learn to remember what is important? The LSTM keeps track of two states, a long-term state, C, and a short-term state, H. It has three important gates, the forgot gate, input gate, and the output gate, which all controls the flow of information and helps decide what information to remember. We briefly discussed RNNs and LSTMs and how they can be useful for sequential data. Try to answer some of these conceptual questions.